Chapter 4, Section 2, Area. Now, in this section here, we're going to consider the classic problem of calculus that we spoke about earlier on, about the area under a curve. Remember, there are two branches of calculus. There's differential calculus and there's integral calculus. The tangent line problem was for differential calculus, whereas the integral calculus was introduced by using the classic problem of finding the area under a curve, which is difficult for us to do, especially with our limited knowledge of area formulas and such. So to do this, we're going to use approximations that involve sums. So we're going to do a quick review here, a little bit about sigma notation and certain types of special sums and some properties of sums. Sigma notation, or summation notation, I like to say that because it rhymes, is where you use the Greek letter sigma to represent a sum. So it says the sum of n terms, a sub 1, a sub 2, a sub 3, and all the way up to a sub n is written as the sum, this is how we read this, the sum of, as I goes from 1 to n, of a sub I, which is a sub 1 plus a sub 2. So you start with the lower limit of summation, or the lower bound of summation, plug in, and you work your way up to the upper bound of summation. This is called the summand right here. And I is the index. Now, they usually use the letter I or the lowercase letter n, or sometimes a lowercase letter j or k to represent that. It doesn't matter. I use I most of the time. So this is the sum as I goes from 1 to n of a sub I. So we start with the lower bound, we plug 1 in, a sub 1, and then we go to the next a sub 2. We just increase by 1 all the way till we get to the upper bound here. And again, I is called the index, or the index of summation. A sub I is the ith term, which we sometimes just call the summand. That's the part that we're taking sum of. And the upper and lower bounds there are the numbers here, n and 1 respectively. So let's find each sum. Now to do this, I start with the lower bound, which is a 1, and I plug 1 into the summand, or into the ith term, and I get 1 plus 3. And then I add to that what I get when I plug 2 in. And I get 2 plus 3. And then I get 3 plus 3. And I get 4 plus 3. And 5 plus 3. And 6 plus 3. And 7 plus 3. And 8 plus 3. And 9 plus 3. And all the way up to 10 plus 3. Good thing it stopped at 10. And what I've done is I've taken the integers from 1 to 10, substituting in one at a time, starting with the lower bound, working our way up to the upper bound here, or the lower limit of summation, upper limit of summation. So what I have here is 4. I got to be able to add 1 plus 3. I have 4 plus 5 plus 6 plus 7, all the way up to 13. So let's see. This would be 9, 15, 22, 30, 39, 49, 60, 72, 85. Hope I did that right. I added those up in my head, so hopefully I did that right, and of course you can tell me if I did it wrong here. Now, as it turns out, we know a little bit about sums from our pre-calculus days. So in this case, there's a common difference of 1. You're adding 1 each time, so this is an arithmetic series, and we could find that the sum of these 10 terms of the arithmetic series was equal to, let's see, it was the number of terms times the first term, the quantity of the first term plus the nth term, and that was all divided by 2 if I'm not mistaken. So this is 10 divided by 2 is 5 times 17, yep, 85. I did do that one right. Now fortunately for me, the next one is a little bit faster, although I'm going to have to plug in my limit of summation. My lower bound here is starting with a 0. It doesn't always start with a 1. It usually starts with a 0 or a 1, but it could start with any integer. And I plug in 0 here, so I would get 0 squared plus 4 times 0. And then I would get 1 squared plus 4 times 1. And then I would get 2 squared plus 4 times 2. Then I would get 3 squared plus 4 times 3, all the way up to my last one here, which is 4 squared plus 4 times 4. So I get this sum. This is 0 plus 5 plus what? 12 plus 21 plus, what's that going to be? 32. So that's 17, 38, 38, and 32 is 70. At least I hope it is. So I have the first two. Now I can get actual sums, or I can get actual amounts. As you'll see in the next example, it's going to be more of an expression because my upper limit is not a value here. It's represented by n. So this is adding the first n terms. So I have 1 over n, and then I plug 1 in here for I, so that'd be 1 squared plus 2. Plus then I have 1 over n times 2 squared plus 2. And I have 1 over n 3 squared plus 2. And 1 over n 4 squared plus 2. Whoops, excuse me, plus 2. And I continue this till I have 1 over n squared plus 2. Now, other than the fact that I could factor out a 1 over n, and that would be what? 3 plus 6 plus 11 plus 18. And I would continue this all the way up to n squared plus 2. And that's about as good as I'm going to be able to get that guy. All right, now, the reason you're seeing this type of an example is because we're going to use that when we determine some areas under the curve. We're going to use expressions that look like this, and we're going to take the sum. I know it doesn't sound like much now, but it's getting there. So hang in there. One more. The sum is k goes from 1 to n of f of x sub k times delta x. So this would be f of x sub 1 delta x plus f of x sub 2 delta x plus f of x sub 3 delta x all the way up to f of, actually I put the 3 dots in the middle like that because I'm lazy. The 3 dots actually go down here below. Okay, if you put them in the middle, I can live with that, but I mean that's where they belong. And this would be f of x sub n times delta x. And again, I could factor out the delta x there if I chose to. F of x sub 1 plus f of x sub 2 plus f of x sub 3 and so on plus f of x sub n times delta x. That looks kind of cool. All right, now a couple properties and some special sums, some formulas that we can use. Okay, we have the linearity properties. The linearity properties, we have those for differentiation and integration. They have to do with the fact of multiplying by a scalar or sums and differences. So in this case, the sum as I goes from 1 to n of a constant k times a sub I is equal to the constant times the sum as I goes from 1 to n of a sub I. You have to think about this. There's going to be a factor of k in each one of them, so I can factor that factor out just like I did on the previous two examples. And in here, this is the sum of a sub I plus or minus b sub I is equal to the sum as I goes from 1 to n of a sub I plus or minus the sum as I goes from 1 to n of b sub I, which is kind of cool because in this case, if we think just about the top sign, the addition, we have the sum of a sum is equal to the sum of the sums. Yeah, think about that. It just blew your mind. All right, now these summation formulas are pretty straightforward. This is for adding up the same number n times. Well, when you add the same number n times, that's just repeated addition, and that's multiplication. So you take that number times the number of times you're adding it, times n in this case. So the sum as I goes from 1 to n of c is c times n. Now this guy is kind of famous, and you may remember this from our pre-calculus days when we talked a little bit about Carl Friedrich Gauss, the prince of mathematics, who as a young child was told to add up the first, I think, 100 numbers or 1,000 numbers, and he was able to derive a quick way to do it using essentially this formula, because that's what we're doing here. We're adding up the first n whole numbers. You're plugging in 1, then you're plugging in 2, then you're plugging in 3, all the way up to n. So it's 1 plus 2 plus 3 plus 4 all the way up to plus n. And it's equal to the number of terms times 1 more than the number of terms divided by 2. Now, these two, pretty straightforward. These two, I don't know if you've seen these guys before. They're worth using and remembering, although they're tough to remember. This is for adding up the first n whole numbers squared, and this is adding up the first n whole numbers. I shouldn't say whole numbers. I should say natural numbers because we're starting with 1. The first n natural numbers cubed, first n natural numbers squared. So these formulas would be useful to remember. I'm going to try to show you an example where we can apply this. I'm asking you to evaluate the sum. Now, I don't want to plug 1 in and 2 in and 3 in and 4 in, and then all the way up to n, where it's going to get kind of weird. But I can use these two properties to break this into, I'm going to kind of double steps up here a little bit. I have this, I have this, I have this, I have these sums and differences. So each individual, and then I'm going to pop the constant out in front. I'm going to write this as 3, the sum, as I goes from 1 to n of I squared, minus the sum as I goes from 1, the sum here, as 1 to n of I, plus the sum as I goes from 1 to n of 4. Now, using this formula right here, all of this is this, so this is 3 times the quantity of n times the quantity of n plus 1 times the quantity of 2n plus 1 divided by 6. Oh, I can see some stuff simplifying there. Minus, now this is just going to be this guy, n times the quantity n plus 1 divided by 2, and then of course this is going to be, with the constant, this is going to be 4n. So let's see, this 3 cancels with that, that's a 2. I have a 2 here. Let's see what I can do with this here. Bring it way over here. This is equal to, try not to tip it too much here. Let's see, this is 2n plus n, or excuse me, n squared plus n, times that would be 2n to the third, all right, plus 2n squared, let's see, plus n squared plus n all over 2. I hope I did that right. Over here, this is going to be minus n squared plus n all over 2. And then, of course, this is 8n all over 2, getting a common denominator. So I have, these are like terms. I have 2n to the third plus 3n to the second plus n minus n squared minus n plus 8n, all divided by 2. What a mess. What have I gotten myself into now? So this is 2n to the third. That's going to be here like terms. These are going to cancel actually. Like terms here would be plus 2n squared plus 8n divided by 2, and I end up with n to the third plus n to the second plus 4n. So I get a simpler expression here for my sum by using these properties and the summation formulas. Now, there's a reason for all this, and that gets us back to the area, the idea of an area. Finding the area of a polygon is fairly easy because we can break a polygon into triangles, and we have a formula for finding the area of a triangle. It was Archimedes that approximated and then determined the area of a circle, which is our most basic curve, the one that we're probably most familiar with. And of course, this is back 287. He lived 287 minus 212 BC, so that's back a ways, well over 2,000 years ago. And he was able to use a limit of an inscribed polygon by adding more and more sides, so you got a better approximation. Now we're going to kind of use his approach, and we're going to find the area. Look at the diagram that I have here. We're going to find the area under the curve above the x-axis between the x equals a and x equals b. Now to do that, our first step is to partition. Now what does that mean? That means we're going to break up the interval from a to b into subintervals. And we're going to make all the subintervals the same size. So I just drew one out here. I have 1, 2, 3, 4, 5, 6, 7. I have 8 subintervals. Okay? Then we're going to either inscribe or circumscribe rectangles looking at what we have here as vertical lines. I'm going to try to draw this halfway decent. I should get a straight edge. But I'm going to be trying to get this as best I can without stopping to draw this. And we're going to either use inscribed rectangles. Now inscribed, because of the way my curve is set up, would look like this. And as you can see, the inscribed rectangles, these 8 rectangles, if I find the area of each one of those rectangles and add them together, I'm going to get a halfway decent approximation of the area under the curve. Now it's going to be an under approximation because you can see some gaps here. But if I use circumscribed rectangles, I'm going to use the green here. I'm going to try to anyway. My green is not as dark as it probably should be for you to see it. And think of the rectangles there. You can see I'm going to get an over approximation using the circumscribed rectangles. Now remember, we are breaking this up into equal amounts. So if we have n subintervals, each subinterval would have length b minus a, this distance here, divided by the number of subintervals. Okay? That way we have what we call a regular partition, where all the subintervals are the same size. Now let's try a very simple example of this. It says, consider the curve f of x equals x squared plus 1 over the interval from 0 to 2, and n, the number of subintervals, is equal to 4. Let's find the area, or at least approximate the area under the curve, using inscribed rectangles. Now, I'm hoping that you're going to be able to see this, but I'm going to kind of sketch it up here. Okay. Hopefully you can see that all right. And I'm going from 0 to 2. So let's say 1, 2, and then I'm going to have to make a slightly smaller scale. 1, 2, 3, 4, 5. And I'd be looking at this curve here. And I'm going from 0 to 2. And I'm going to break this up into 4 subintervals. So 4 subintervals of equal size, that would be 2 minus 0 divided by 4. Each one would have width 1/2. So I could mark here a half, here at 1, here at 1.5, and then here at 2. And I am going to use inscribed rectangles here. Now I have an increasing function. My function is going up and to the right. So when I draw this in, I believe you will hopefully agree that all my inscribed rectangles, the maximum value occur at the left endpoint, because that's the smallest value down here in this subinterval. So they're all going to occur here at the left endpoint, and this is going to be an under approximation. So I am going to get the sum here. I'm going to write, usually for inscribed rectangles, because it's an under approximation, they use a lowercase letter s and then a subscript of 4. For an over approximation or circumscribed rectangles, we use a capital S and then a subscript for the number of subintervals here. So this would be, now I'm going to go base times height, and all my bases are a half, because that turned out to be what we typically call delta x here, is 1/2. So that would be 1/2 times, well, it's this value here. It looks like it's a 1. It's the y value when x is 0. So this would be f of 0 plus 1/2 times f of 1/2. That would be at the next left endpoint for this guy. So then for this guy here, this would be 1/2 times f of, this would occur at 1, at the 1 value here at the left endpoint, and then 1/2, that'd be this guy. And then 1/2 at the left endpoint, that'd be 3/2, or 1.5, so that'd be times f of 3/2. So this is 1/2, f of 0 is 1, plus 1/2 times f of 1/2 would be 5/4, plus 1/2 times f of 1 would be 2, plus 1/2 times f of 3/2, that would be 9/4 plus 1, which is 4/4, that'd be 13/4. I hope I've done this right. So this is 1/2 plus 5/8 plus 1 plus 13/8. Well, 5/8 and 13/8, so you have common denominators. That's 18/8 or 9/4 plus 2/4. 9/4 and 2/4 is 11/4 plus 4/4. This is 15/4. And this would be square units because we're finding the area. And that would be an under approximation because I used the inscribed. Now it says find the area of the curve using circumscribed. Well, let me go back to my diagram here and use a different colored pencil here. And so all my y values, my heights, are going to occur at the right endpoints of each of the subintervals. So I'm going to get a very similar looking sum. I'm going to use capital S sub 4 because I'm going to use 4 subintervals. And I'm going to write this as 1/2 times f of 1/2 because it's occurring at the right endpoint here, plus 1/2 times at the right endpoint here. That would be f of 1 plus 1/2 times f of 3/2, and then plus 1/2 times f of 2. Now, I didn't do it in the first example, but I most certainly could have just factored out the 1/2. I probably should have and saved myself a little bit of aggravation. If I plug a half in, I get 5/4. If I plug 1 in, I get 2. If I plug 3/2 in, I believe I got, let's see, what was 3/2? That was 13 fourths. And then if I plug 2 in to my function here, I get 5. So 5/4 and 13/4, that's 18/4 or 9/2. So I have 1/2 times, now I have 9/2 plus 7, which is 14/2, that's 23/2. So I get 23/4 square units. So you can see that this number is smaller than this number. This was an under approximation, this was an over approximation. I'm thinking that my area, the actual area, is going to be somewhere in between S sub 4 and capital S sub 4, between my lower sum and my upper sum. And that's what they refer to these as, the lower sum and the upper sum, lower using the inscribed, upper using the circumscribed. Now, in more general terms, if we don't have a specific number for n, if we just let n be whatever the number of subintervals represents, then we have some notation for you to kind of see here, where f of m sub I is the minimum value of f of x in the ith subinterval, because it doesn't always occur at one of the endpoints. It does if it's increasing or decreasing function. F of capital M sub I is the maximum value of f of x in the ith subinterval, so this would be used for the lower sum, this would be used for the upper sum. Delta x is b minus a over n. I kind of showed that. That's the width of each subinterval because it's a regular partition, all the same. S of n. Now, sometimes they use subscripts. Sometimes they'll actually use kind of looks like set note or function notation. Is the lower sum because it's a smaller case letter s, and capital S of n is the upper sum. So what I'm going to try to do here is, and I've got this all written out for you, so I'm going to kind of walk you through it. But I'm going to use an increasing function here, f of x equals x squared over from 0 to 2. So it's similar to what I just did, except that it's been dropped down 1 unit because it's just x squared instead of x squared plus 1. And I've got the diagram right here. And I'm going to find the lower sum. Since it's an increasing function, they all occur at the left endpoint. So lowercase letter m sub I is the left endpoint at 0 plus I minus 1 times the length of my subinterval. My subinterval is 2 minus 0 over n, or 2 over n. So to go to the first one, that would be 2 over n. Now I want the left, if this is my subinterval, so that would be 2 over n, but I want the left endpoint, so it's 1 less than that. So if I plug in for my first, it's going to be happening at 0. And I can use this, I simplify this, and I get 2 times the quantity I minus 1 all over n. So the sum, as I goes from 1 to n of my, these are my minimum values times my delta x, that would be f of this expression in for m sub I, and then of course 2 over n in for delta x. And then I actually find f of this by taking all of this and substituting it into the rule, so I have to square it. And I do some calculations, and I get 8 over n to the third times the sum, because 8 over n to the third. N to the third is not affected by, doesn't have the I index in there, and this is be my ith term. And then I use those formulas for and properties of summation, and for special sum formulas, where I have I squared, and then I have the I, and then I have the constant. So that means that I have to come over here for the I squared, the I, and the constant, use the formulas that I gave you before, do a whole bunch of algebra, and I get all the way to this. That's an 8, by the way, right there. And that would be the sum of all the inscribed. If I change it slightly and find the upper sum, it turns out it's the same exact thing, except where this was a minus, this is a plus. And I'm telling you that the area is between the lower sum and the upper sum. Okay. Now, would I expect you to do a bunch of these? Oh, probably not. We need something that's going to help us so we can streamline our work. For right now, though, this is what we have. This is how it's set up to approximate the area under the curve. Now, we're going to use this approximation and a limit, as you might guess, and we're going to get an exact value. So, here's our theorem. The theorem of the lower and the upper sums. There we go. Let f be continuous and non-negative on an interval from a to b. The limit as n goes to infinity of both the lower and the upper sums exist. Then the area, and are equal, I can't even read my own writing, to one another. So if the limit of the lower sum is equal to the limit of the upper sum as n goes to infinity, then this is equal to one another, and that this means that this would give you the exact area under the curve. It has to be in between them. Well, if they have the same limit, then the area is going to be that limit. And of course, all this notation I showed you before. So from above, if I take the limit of the lower sum, if I take the limit of the upper sum, as n goes to infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0, I get 8/3. That's my actual area, 8/3 square units. And you have to kind of trust me on the circumscribed rectangles. I've done it before, I just didn't show you the work this time, so kind of bear with me on that. Now, the area of a region in a plane, if f is continuous non-negative on the interval from a to b, the area of the region bounded by the graph of f, the x-axis and the vertical lines x equals a and x equals b, is equal to, now notice this is very similar, it's the limit as n goes to infinity as I goes from 1 to n of f of c sub, that's supposed to be an I there, you can't hardly tell, times delta x, where c sub I is any value in the subinterval, including an endpoint. It doesn't have to be at a particular spot. It doesn't have to be the midpoint or the endpoint. So what this is saying is, as long as I pick a value that's in the subinterval and plug that in to find my height, and that of course is going to be my base, I can find the actual area by taking the limit as n goes to infinity. Because as n goes to infinity, the number of subintervals increases without bound. That means each of the subintervals is getting smaller and smaller and smaller. And what that would mean that x sub c sub I, it doesn't matter what number, we're going to find the exact area. All right, I have one more somewhere. Did I leave it? I probably left it at my desk. Heavens, the Murgatroyd, I think I left it at my desk. Well, I have my rough copy. I hate to show you that because it's all beat up and it's sloppy, but we're going to go ahead and show you. Here's one last example, and you can see my scribbles all over this thing. I hate to show you this one because it's such bad handwriting that I have. So find the area of the region bounded by the graph of f of x equals x to the third power with the x-axis and the vertical lines x equals 0 and x equals 2. It doesn't matter what x value we pick from each of the subinterval. So for convenience sake, between 0 and 2, if we partition in n subintervals, each of the lengths of the partitions would be 2 minus 0 over n, or 2 over n, and I'm going to pick the right endpoint. The right endpoint, so I don't have a minus 1. So c sub I is equal to 2 times I over n, because here's 0, this is 2 sub n, so this is 2 over n times 1, 2 over n times 2, 2 over n times 3. The right endpoint is 2i over n. So the area would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of c sub I times delta x. And then I'm going to plug in 2i over n in for c, and I'm going to cube it. That's where this comes from. And that's my delta x. And I'm taking the limit as n goes to infinity. So now I took this, I cubed it. So I have 2i times 2i times 2i, 8i to the third over n times n times n, n cubed. So I am taking, this becomes, and then I have a 2 here, this becomes, this part becomes 16 over, 16i over n to the, that would be 3/4 power. So I popped, I don't know why I popped originally, didn't put the 8 out there as well, but I guess because I didn't think about it. So I brought the 8 and the 2 out here, that's 16, that's this part right here, and I have the I raised up to the third power. So that's that formula for taking the sum of the first n natural numbers cubed, which is n squared times the quantity n plus 1 quantity squared over 4. I multiplied it times the 16 over n squared. This is really sloppy, I apologize. That's a 4 there. So I have 4 over n to the 4th times this. Now I multiplied that out, and I multiplied it distributed by 4 over n to the 4th, and I got this. And then I simplified by dividing the n to the 4th into both, or into all three of the terms in the numerator, and I got 4 minus 8 over n plus 4 over n squared. As n goes to infinity, this goes to 0, this goes to 0, and as you can see here, the actual area under the curve, this curve above the x-axis between 0 and 2, above the x-axis, turns out to be exactly 4 square units. So there is a little bit here, and I'm going to have you try a couple problems where you're finding lower and upper sums, but most of it's going to be where n is going to be a finite number, like let's let n be 4 or n be 8, so that you can find an exact number instead of having to go through this limit process. But you're still going to need to practice these problems, and of course ask questions if you're unsure.